everybody has the same problems, and that's the distribution of trust. How do you trust unmanned devices, millions of them out in operation? And how do you coordinate them? How do you get them all working together?
Welcome, everyone, to the Industrial Security Podcast. My name is Nate Nelson. I'm here with Andrew Ginter, the Vice President of Industrial Security at Waterfall Security Solutions, who's going to introduce the subject and guest of our show today. Andrew, how are you?
I'm very well, thank you, Nate. Our guest today is Dr. Christopher Gorog. He is the CEO at BlockFrame, Inc., and he himself is the host of the new Cyber Frontier podcast. And he's talking to us today about establishing trust, distributing security credentials in large industrial operations.
Then, without further ado, here's your conversation with Dr. Gorog.
Hello, Chris, and welcome to the podcast. Before we get started, can I ask you maybe to give a few words of introduction about yourself and about the good work that you're doing at BlockFrame?
Yeah, thanks a lot, Andrew. My name is Christopher Gorog. I am a PhD in cybersecurity. Just recently finished my degree, where I worked on the distribution of trust by all means of other things, blockchain, what we call distributed ledger. But my background has been in cybersecurity. I host the new Cyber Frontier podcast, which we have over 400 episodes, been running 9 years, probably one of the largest followed out there. I chair digital privacy for IEEE for a global initiative, among many things, hold several patents, and my work with the University of Colorado and the state of Colorado to help support legislation in the area of privacy and security. So a lot of things we'll get into as we unpack in today's show.
Our topic today is trust, distributing security credentials in large industrial operations. Can you talk to me a bit about the problem? What is a large industrial operation? What does it mean to distribute security credentials? Why is this important?
Yeah, Andrew. So that's the ultimate question, the problem set that I've been solving or working on literally my entire career, because even in early stages of my career, working with many different vendors that are implementing security, everybody does it a little bit different. Everybody has the same problems, and that's the distribution of trust. How do you trust unmanned devices, millions of them out in operation? And how do you coordinate them? How do you get them all working together? And then how do you secure them becomes a function of that trust once you can distribute it. We have several methods of distribution of trust using certificates and PKI, which the part that we have a problem with is the human part. The people that own the trust authorities, the certificate authorities, the people that we have to rely on, and they don't trust each other, they don't work together, they're different governments, they're different companies, and we have a disjointed. So looking at solving the problem industry-wide is what I've been approaching literally for, some of my work started in 2006, 2007, working with SGIP and the Smart Grid Interoperability Panel, where you'll find me on the cryptographic key management of the NIST 7628 IR as one of the initial authors, where we put together, what is needed for cryptographic key management. Back then, we didn't have the global recognition of the tools that we know in blockchain. So my work in my dissertation has been in trying to solve the problem of trust distribution by taking care of the human needed pieces using distributed ledger and making that work. And that's what the focus has been. And I think we have some great solutions where we can show now feasible, global, attainable, scalable problem solutions in that area.
And, to clarify, you've said millions of devices. I mean, I understand cell phones. I understand smartwatches, millions of these things. In the industrial space, to me, when we're talking millions of devices, what leaps into mind is the smart grid. It is, smart meters. It is advanced metering infrastructure, whatever the buzzword of the day is. Is that what we're talking about here, or are there other applications?
Yeah, absolutely. We're talking from the smallest sensors to even PCs and servers. So all across the board. And that's one thing. For years, I worked with a semiconductor manufacturer in placing and putting cryptology into many different vendors' devices. And in that realm, there's literally like 100 16-bit processors made for every 32-bit processor, and there's like 1,000 8-bit processors made for every 16-bit processor. So the smaller the devices, the more of them there are out there, and that's the problem. We have relatively efficient solutions for the computers that humans sit behind. But the millions and billions of devices that are unmanned on the grid that communicate as a mesh that we might just read on off temperature, power from 100 times a day or even an hour, that's really where the problem is in that mass amount of devices out there.
So Nate, I'm thinking back. I remember a few episodes ago, there was a gentleman on talking about the CAN bus. I'm not sure I remember his name, but that's the bus that's in automobiles.
I think this was Ken Tyndall.
Yes. And, his observation, a truism in the space, is that encryption is a tool for turning every problem into a key management problem. And I think this is sort of another example of that principle that we're seeing here. We're talking about blockchain, we're talking about cryptography, we're talking about authentication so that devices can prove they are who they are. And all of that involves managing keys. It involves more generally managing trust. And the application that springs to mind, the first place I saw this in the industrial space, a decade ago, was in the context of smart meters, power meters on every consumer's home or apartment, billing appliances. And we're talking big systems. We're talking, a power distribution system in a city with, 3 million smart meters. And as Christopher pointed out, there's other really big systems out there. So, what springs to mind is if you're monitoring, let's say, a water treatment system, and you want to know what's coming at you in the watershed, you might have rainfall sensors, you might have, water level sensors spread in thousands of locations throughout a massive, 300, 500 kilometer wide and long watershed. You might have weather sensors throughout, a whole country gathering data for weather prediction. You might have smart cities. You might have traffic sensors everywhere. And, his point that, yes, there are sort of big computers, 32-bit, 64-bit processors in these systems of, thousands, tens of thousands, millions sometimes of devices. There's very few of those sort of big conventional computers analyzing the data. Most of what we're talking about here are very small. He's talked about 8-bit and 16-bit, talking about compute capability. In a lot of these circumstances, out in the middle of nowhere, there is no electric power. You're talking solar-powered devices. You're talking not just limited compute power, but limited electrical power. This is sort of the big picture of the problem that Christopher's going to be talking about.
And when you put it like you just did, it occurs to me, on this podcast, we're usually, not exclusively, but usually talking about, manufacturing plants, refineries, hospital. These are sites where you sort of have a boundary around them, for better or worse. And most of it is indoors, maybe not entirely. It's like a controlled space, but as you just mentioned, when you're talking about smart meters or traffic sensors or what have you, these are really widespread outdoor sort of everywhere situations. I would wonder how this affects the security problem. And I'm sure that you guys are going to get into that.
The main problem I heard you describe here was key management. And, I've heard encryption described as a tool that turns every problem in the world into a key management problem. What is the key management problem when you're talking about, I don't know, traffic sensors or smart meters? Can you give me an example? What's the problem? Why do we need a solution at all?
I said cryptographic key management. Some people might call it trust management, root of trust management. It's the pieces in the center of your every device. And if you have an energy meter, for example, and a company makes a model, and then they mass produce a million of them, the software is exactly the same. The only thing different is the serial number in there that tells it which one am I. But now in the age of virtualization, you can have a virtual machine running a simulated software meter, a real software meter, and if they're all on the internet, you can't tell the difference. So some people might say the root of trust is an identification problem, and each device being able to identify itself, but to also uniquely say that I can not only identify who I am, but I can prove that I made this operation. I produced this data. I communicated with this other device, and the two devices can prove each other and say, I'm actually talking to the device I'm supposed to be talking to, and not a virtual device that's mimicked of it, or some other device, or somebody is in between listening. All those pieces in security that make each device, and I know this gets kind of in the conceptual level, but when we move it down to an energy meter, can all my energy meters on my grid verify that I'm talking to them from my reading station, verify that when they're talking to each other when we're collecting the data, and that the data is accurate and actually came from them, so that we can then have valid information for billing, or valid information for our control structure, or for our demand response. But all of the information that comes to and from any embedded system that people might not touch for 10 years becomes questionable whether it's authentic, or whether it's valid, or whether we're even talking to the device we are with the interconnected age.
What is the risk here? Let's say that I have, found on the internet someone has stolen a copy of the firmware for the smart meter that is in my home. I put it up in a virtual machine, and now I'm impersonating a smart meter. I, in principle, can find the serial number on my device because it's there attached to my home, and I, can embed it in the virtual machine, and now I can, disable somehow, put, tinfoil around the meter, disable communications between the meter and the grid, and now I can impersonate the meter and say, Andrew's not using any power. Is that what we're talking about? Is that the attack scenario, or, is there something else you're thinking about?
So when you're looking at a meter, the attack scenario is the company protecting itself from the customer, and I think that's kind of what you were alluding to. When we get into the day and age that everybody's a producer and a consumer, and microgrids and power is coming onto and off the grid by different people at different times of the day, different providers, the meter becomes your proof of whether you took power or provided power to the grid. And if you, as a utility company, have a whole bunch of customers out there that are telling you they're providing power to your grid, and you now are expected to pay them, how do you prove that they're accurate? Is the question we're answering here in that case. It's not as important if all the meters are owned by the company, other than to get an overall, we're not getting falsified. But when we get into that now, renewable peer-to-peer energy ecosystem of microgrids, we can't trust the people. If we can't trust the people providing the information from a microgrid to make monetary transactions based off of, we end up with anybody being able to scam the system indefinitely, because you can't prove that they put power on other than their communication, which if their communication is not provable mathematically, cryptographically, and that's what this root of trust in the distributed devices gives you.
To me, clearly there's a need. You've convinced me there's a need to identify these meters, especially if they're putting power onto the grid. I mean, partly billing, yes, but partly if you've got enough of these things, there's grid stability that might be at risk. But is the solution not that when the technician shows up at my home to attach a meter to my house, is the solution not that the technician writes down the serial number and, presumably there's a database somewhere associating serial numbers with private keys that are, built into the device. Is that not the solution? Why do we need something more complex?
So the solution, if you think about what you just said, where the private key of the device, right? And the solution set isn't the private key in the device. It's getting the private key to the device. And if that's somebody doing it every time a vendor puts one on the grid, there's 50 different vendors that makes products for it. Everybody does it differently. And everybody has a different certificate authority if they're using certificates. And the certificates can be changed. They can be stolen. They can be spoofed. In a virtual machine, you can imitate another machine entirely. So if we scale back and step back and say, yeah, the meter set is one problem in the consumer base, and we're moving towards that distributed consumer producer environment. The bigger problem, at least the now problem, is in the control structure, the demand response and the infrastructure of control, and that they have equipment made by many different vendors that go into this, and they have to have microsecond responses from trusted equipment. And the only way to do that is to keep it on a private grid, private network. And each utility company now wants to start interconnecting and working across utility companies. They have hundreds of thousands of devices that a human might not touch for 5 or 10 years. And keeping and maintaining those keys that you just talked about, the private keys in every device, is a human-centric problem, and that's where we're falling short. What we're talking about here is modularizing and making that human solution done uniformly, to have their cryptographic keys managed so you can see them, not just for a grid, not just for a utility company, but for the industry. Many different companies, many different vendors that all come in and put products in this kind of Frankenstein mesh, and all of them are different, and all of them are done by different people who we might not know, might not trust, different levels of software, different levels of responsible people, even maybe something made in a supply chain where it was in another country and there's purposeful harmful information or malware injected into it. So that mess of unpredictableness is the problem that really is plaguing that whole industry. We are all working in our own space without the ability to know that who we're talking to and what we're putting on our networks and into our systems is actually authentic.
Okay, so, that kind of frames the problem for me. We're talking millions of devices on the grid. Some of them are measuring power consumption. Some of them are measuring power production. Some of them are measuring other things. There's a lot to measure when we're talking about that level of granularity. And yet, while I take your point that there can be manual intervention in the course of deploying the equipment, it could be from lots of different vendors. And if it's going to sit there for 5 or 10 or 15 years, the way this stuff often does, when was the last time you updated the firmware in your refrigerator? If it's going to sit there for a long time, these keys age. Best practice is that, especially on the internet, you don't leave the key in there forever. There's got to be a way to update these and, coordinate the updates across, producers and consumers of the information. Then it all makes sense that this is a problem. You've got a technology. Can you talk about the technology? What kind of technology are you proposing as the solution to this problem?
Yeah, so from an industry level, working with many different vendors, and literally 15 years, 20 years of my career has been working to solve this problem, is identifying what are all the things that they have been doing. And the first part was to create a modular piece that could go into any device that would handle all the things that everybody is using for security, and simplifying it. The interesting thing is we overcomplicate what is being done, and we make 1,000 different applications. But security is kind of like an art form as much as it is a technology, where in artwork we only have 9 components that make up paintings and pictures and sculptures. And artists learn these in college, and once you can master each one of the 9 components, like line, form, volume, shape, parallax, there's 9 of them. Cybersecurity, similarly, there's only 7 things we do. And people might challenge this, but we identify data, we authenticate users and systems, we establish connections, we hide data or encrypt it, we log and operations and verify the data in the operations, and we distribute trust. I think that was 7. So if we make a way to unify the ability to do all those, we can put that modular approach into every system, every vendor, every product. And then the second thing is to make a way to change that out, because we know that we can't keep the same security forever. So the second part of what we do is a method using distributed ledger known as blockchain to be able to change out those credentials, the human piece that we usually do with a guy running in the truck to it, and be able to do that and prove that it was done globally so everybody sees it. So we can prove who it basically is responsible for that provisioning, it's called, of those cryptographic components. And it doesn't have to be somebody that you don't trust. It's open. And this is where we kind of borrowed that distribution of trust using blockchain, what we know from like cryptocurrency, but using it in a totally different way to actually distribute the root of trust, the cryptographic keys, which are all standard cryptography, just doing the human aspect, but proving that and proving the provenance of it, the attestation of how that happened over your whole grid, over every product, or over your supply chain throughout the life cycle of the product, and maintaining that over time and over distributed area and over geographic and over logistics of networks, and even the people aspect of it, connecting your workforce and maintenance.
Andrew, we've done somewhere north of 100 episodes of this podcast at this point. Are there really only 7 steps to industrial security here?
I should have asked. I was kind of wondering that myself. I did a quick Google afterwards. I haven't seen where the 7 steps come from, but if you ask me, those are 7 steps that are integral to communications security. And we've been doing 100 episodes. We're talking about the big picture is more than communications. It has to do with physical security. It has to do with, people, process, and technology. It has to do with host-based, a lot of host-based stuff, as well. Concrete example. If I've got a host. I've got, it's a I don't know, Windows box, a Linux box, a server, 64 bits, big operating system. And it turns out that my crypto library has a vulnerability in it. And that vulnerability can be exploited simply by sending a message across the internet into the machine, into the host, into the server. And that compromises the library. It makes it, buffer overflow. It makes it do bad things. No amount of key management is going to solve that vulnerability problem. That's a patch problem. So if we're talking about pushing data across the wire, if the receiver, the server, is asking the question, can I trust the data? Well, then the 7 things that Christopher's talking about here, these are all steps that we do have to have in place. But the bigger picture is there's a little bit more to it. So that makes sense. I mean, we need to change these keys from time to time. We got lots of different vendors and, power utilities and others involved. When we make a change to the key somewhere, we have to publish that. That publication mechanism has to be standard so that everybody can consume the knowledge that we've just changed the key. Everyone who has to communicate with this device. We have to make sure that process is authentic, that it can't be spoofed by someone trying to, steal power or, do other malicious things. And the solution that you're proposing is blockchain. So can we talk about the solution in a bit more detail? I mean, Bitcoin is power hungry. Bitcoin, there's farms of servers involved. It's not going to work with an 8-bit CPU. What does your solution really look like?
There's a lot behind that simple question. And it comes, in two parts. One, the part that we're provisioning is very tiny. And literally the cryptographic keys and the continued operation only takes up 64K of memory in a small sensor device. So now we look at that's what goes out, and that's the key distribution. That's what goes on your device. It doesn't take much size. Now, the distribution of blockchain was a whole nother problem set. This actually, I spent the last 6 years, my PhD dissertation, in solving the problem of scaling blockchain. And we actually threw out traditional blockchain. That's why I always try to say we have a distributed ledger. We now are going to the third generation of the first generation was cryptocurrency. The second generation was smart contracts and your Ethereum, your Hyperledger Fabric. And now we have a third generation that doesn't use the mining, a different algorithm that turns around the work to be your time spent participating, storing data over time is how you gain your incentive versus a wasted energy up front. And we're actually running peer ledger, distributed ledger nodes on a Raspberry Pi. That's how small they can run on. And then it's designed modularly so it can expand indefinitely, where we have a consortium that's similar to your DNS on the internet that manages who's out there and the governance of it. And then each individual peer that can scale horizontally like your routers on the internet. And we're turning into this new animal of no mining and indefinite scalability. I think it's, I'm excited about it, but it's been my 6-7 years of work. And, I'd love to help anybody understand more about it, bring in, ask questions, as much questions as you want. My dissertation is out, publication. You can find it under Sustainable Framework for Distributed Ledger is the title of it on ProQuest, and it's open for anybody to view.
Let me dig just a little detail deeper. You talked about the memory footprint in the device. You talked about the Raspberry Pi is managing the ledger. Something you didn't mention is the size of the ledger. I mean, in my understanding, the Bitcoin ledger is now like a dozen terabytes or something like that. It's and that's that's money changing hands. If we have millions of devices coming out of each of dozens of vendors going into, hundreds of power utilities all over the world, most of which are connected to at least one other power utility. There's very few power utilities that operate in complete isolation. It seems to me that, is it the case? Let me ask you, is it the case that you have to be able to share all of this key information for every device on the planet with every possible consumer on the planet? And if so, is that going to scale sort of storage wise?
And that was actually the problem we set out to solve, because whenever we came up with the modular approach to distributing cryptographic keys, we actually tried it on some second generation blockchains and used Hyperledger Fabric, Sawtooth Lake, and Ethereum. And it brought it to its knees. There's no way either any of them could scale. So the whole design of a scalable blockchain was based on being able to hit the mark of the needs for cryptographic key management and how big that would get. And basically, we came up with a loosely coupled chain of chains. So side chains that operate independently. And that's what I said, like a router, like a set of routers you plug in, and they all work together, but not everybody has to have everybody's data. There's subsegments, and it makes it scalable, but yet it's the same forensic mapping to prove everybody's transactions and timestamp them globally. And it's a unique consensus approach called a synchronous trust consensus model, where it adds a couple of major things. One, that we no longer have to keep data all the way back to the Genesis block. The data is kept as long as it has value to the operator. And until you get your incentive, which is set for the longest time at about 14 years, but only in subsets of data as well. So not everybody has everybody's data. And the consortium servers keep the validation data of all the individual groups of ledgers that can now scale indefinitely across the globe. My testing, and you can read it in my dissertation, where I scaled this up to 52 million ledgers, which is currently the size of the number of routers on the internet, to see if it would still be feasible and operational. And the scalability models predicted that we could do this. And that the growth in size and even the data we're going to persist over time is manageable because we can phase it out over time and basically have a window moving forward. And that management of data and the ability to meet this mark is and has been that primary focus. So kind of excited, like once again, open to talk more about this, and you'll hear me speaking all over the place on it. But it is really a very involved topic. We've had over 400 people in the state of Colorado involved, over 85 people turn code on community source projects and this has been funded by the state of Colorado under legislation we wrote in 2018 through the University of Colorado, Colorado State University, a couple others. And that's why it's so big and exciting, is we've had so many people work on it and getting excited about it, that this is actually something that we can see scaling to that next generation for solving those problems you brought up in your question.
So, real quick, just a clarifying question. You suggested 52 million routers. You said 52 million ledgers. Does that mean that each ledger could in turn manage thousands or, I don't know, a million devices? And so that's the 52 million times 1,000 or a million that we're talking about? Or is there a ledger per device?
When I'm talking 52 million ledgers, I'm talking the number of ledgers that can store an indefinite amount of blocks, as many as they can handle on the blockchain. So the amount of data transactions is astronomically larger than that.
Admittedly, Andrew, whenever this kind of subject comes up, I become a little bit suspicious. If I had a nickel for every time somebody sold me on a scalable blockchain, I probably wouldn't have to do podcasts anymore. So the question that I suppose I would ask of Dr. Gorog, which may well be answered in his dissertation or later in your interview here, is whether this kind of blockchain solution that he's describing, while scalable and fast and whatever usable as you need, offers the same kinds of security protections or doesn't compromise too much on them compared with the other blockchains that we're using as comparisons. Bitcoin, Ethereum, the ones that are slow and unscalable for reasons that aren't trivial.
Good question. I did not ask that question. I do know that, one difference between the system that Dr. Gorog is talking about and the traditional sort of Bitcoin blockchain is power usage. I mean, the Bitcoin blockchain already uses a measurable fraction of all of the world's power. And we're talking about, a tiny, tiny fraction of all the world's computers involved in that blockchain. Whereas, here we're talking about 8 and 16-bit devices, millions of them in every city involved in this ledger. The second sort of thing is I don't even know if this is the right question to be asking. The Bitcoin blockchain models the movement of money, whereas here this blockchain models trust. It models the degree to which we can trust different devices within an organization, across organizations. I don't even know if these are the same questions. I mean, when we're talking about trusting things, the thing that springs to mind, the system that springs to mind, is Active Directory. It's the classic system that's used for managing users, not even devices. Active Directory doesn't manage devices, to my knowledge. It manages users. And we're talking about, a system that could, in principle, scale to all of the devices on the planet being interconnected to some degree. And I don't know how big Active Directory will scale, but I'll be deeply surprised if it scales to all the users on the planet, much less the 100 devices per user that we're expecting to see deployed in the next century. So, short answer is I don't know. The longer answer is I think it has to do with power usage, with scalability to, sort of ridiculous scales is my understanding. You folks, that you personally been involved in this for a long time. BlockFrame as a company has been involved in it for a long time. Can you talk about BlockFrame a little bit more? What have you got in this space? If a vendor called up and said, "Hey, I want to do this. You've convinced me." Do you have technology? What are you offering in the space?
Yeah, so BlockFrame has been around for 7 years. The technology from my dissertation is wrapped into BlockFrame. We have literally patented the consensus model where we'll be the only ones globally able to implement this. As well as opened up a community project where a lot of this work was done for the state of Colorado, funded under many different sources. And a big piece of it is open source interfaces that anybody can develop on top of to make your community your project for your application. Write your own smart contract, do your own embedded application that implements on top of the distributed ledgers for the blockchain side. Or we also, and BlockFrame offers the modular ability, and whether a hardware insert, a physical device that goes on your IoT device that holds your cryptographic keys, or a modular. We even have a software approach. The hardware is always going to be more secure. That we can work with vendors right now to implement this and get into your design for your next release, or work on getting it into patches that could go out into legacy systems. So we can. We're offering for one cost through the release of your product to get you on board, get you all your tokenization on the blockchain, all your embedded design set up, support with getting your product to market. And we offer that all to any vendor who wants to be an early adopter on this. If you're looking at, hey, I want to be on the next generation of security that's not only modular, but peer-to-peer based. Now, every device can go unique to each other, which opens up that thing that we've been looking for and why people got into blockchain so heavily, because it opens up that peer-to-peer. It takes out the middleman. It makes it so now every one of our devices are individualized and can have a verification of each other, zero trust between any two devices, because they can identify each other on the blockchain before they communicate or commit to any operations, and then do trusted proof of origin signed data between the two of them. So the level of security is something we haven't seen in our day and age, where we're looking at, to date, we've collectivized data. All data is held by a company, an organization. We're looking at this migration to end node, to the edge, to peer-to-peer. And it's just a new paradigm in how we will look at security in the future.
One other thing that struck me in your description of the solution, there's technology involved. There's, sort of a communications infrastructure, the distributed ledger involved. You mentioned that there's patents involved. How interoperable is this? If, a group of vendors on the other side of the planet wanted to do this stuff, I don't know, on their own, could they? Is there a sort of a standard of standards where these many different kinds of ledgers can interoperate? How universal, how universally available is the data here?
Yeah, and so we actually, like I said, we designed this for standardization, for modularization. So every single cryptographic root of trust in all the devices is a modular block. Now, what is in those is entirely different for each one. And your vendor, your product owner for all of their products, decides on certain pieces of it. The industry utility registrar, which is a kind of like a DNS server that provisions a set of products out there, is is able to then uniquely identify each one, and we are licensing those registrars for different companies to use, for different industries to use. So not only is the individual pieces of it modular, the blockchain for the Wayback Machine, you can revert back to a earlier stage that you did trust the device if it becomes compromised and reprovision from that. But now we have the ability for multiple different people, multiple different product owners to take charge of their segment of the market. And we have we actually did a decentralized autonomous organization that owns the rights to run and manage the public distributed ledger. And that's the state of Colorado through the University of Colorado is a part owner in that because many people provided that effort. So the whole thing is designed around these modular pieces that are developed for anybody to build on top. And then even the smart contracts are then become ownership of the person that wrote them, and they can sublet or sell their smart contract for other people to use for whatever price they want. And you have all these modular constructs within the overall system of systems that makes everybody in the marketplace be able to run their own business and be individual. The control structures that we put together is just to make sure that we don't have competing standardization pieces. And that's why we decided to go with the patent route. So we didn't have somebody competing against releasing the same thing on the other side of the world that we can then say from the first couple phases, we get it very standard before we start that kind of push and release structure.
All right, Andrew, we are really getting in the weeds of blockchain stuff, and I'm only faintly remembering that we are talking about smart meters here. Can you help me with the connection?
Yeah, so sure. It's more than smart meters. It's devices all over the place that need to talk to sort of control systems, SCADA systems, sort of high-end analytical systems all over the place. The example in the power grid is, yes, smart meters is one piece of it. It's really, but we're talking about gathering information from many, many devices. And we're talking about sharing information and sometimes even sharing devices between organizations. So it's not just the meters. It's also the devices that are connected to, millions of rooftop solar that are sometimes producing power and sending it into the grid. And, the household is sometimes consuming power from the grid. These who wants to talk to these devices? Well, yeah, the grid wants to talk to the devices, the local utility, but sometimes there's other aggregators like, I think Google has a system now where they can talk to your rooftop solar and aggregate your rooftop solar so that they can, interact sort of more aggressively, more personally, with human oversight into power pricing to maximize the price that householders get for the power they give back into the grid and of course, Google takes a cut of all that money. But there we've got an example of a couple of organizations talking to the same rooftop solar. You've got synchrophasers all over the grid, which are talking about, measuring in a sense, the health of the grid. I won't go into phase measurement, but it's a technical thing that's done. And these synchrophaser measurements make sense to share across the many utilities that are cooperating in the grid. There's load shedding devices that have the ability to shed load that need, instruction from outfits like Google that are maximizing what you get paid for shedding the load, that need to be, connected and report to the local utility and possibly other utilities. You've got high voltage charging stations coming online everywhere that are pulling a lot of power from the grid that need to interact with the local utility and possibly bigger utilities. In traffic, you've got different cities that are, coming up against each other, different jurisdictions. They might not want to know what's coming their way. The simplest way of doing that might just be, connect to some of the other cities' traffic sensors. But now you've got multiple organizations, multiple cities talking to the same sensor. It's all about devices that need to talk to each other, that need to talk to a central analytical station, and where you've got multiple jurisdictions that need to trust, that might need to interact most profitably with individual devices. So it's it's all about sort of the big picture and interoperability. A lot of our episodes on the podcast here are focused on programmable logic controllers deep into heavily protected networks that nobody on the internet has any hope of having a look at. If we're out on the internet, if we're reporting power usage, when we're out on the internet, privacy is often a much bigger factor than it is deep into a heavily protected power plant network. And so I've been asking you sort of questions from the perspective of the industrial security aspect. But, if my power usage is on the internet, I do care about who can see that. Have you got privacy stuff built into this as well?
And that's a great question, because one of the first things I started out looking at security, and cryptographic key management is all about security is what I thought. And then when we started working with the state of Colorado and looking at several different programs, they had over 71 programs, last I heard a list of them, that were candidates for these type of technologies. Each one had different requirements. And I started asking, well, who makes a decision on them? And nobody raised their hand. There's nobody making a decision. When we started analyzing those, they're privacy questions. They're where is it held versus where is it stored? What parts of it are private? What parts are public? Who has opt-in? Is it opt-out? Who's allowed to have access? Who's allowed to audit versus who is allowed to see it? Are you allowed to audit without seeing it, or do you have to know that they audit it? And there's so many legal and privacy questions. And that actually drove me to start asking these questions. We ran a campaign called Privacy for the People literally like 4 or 5 years ago. We got some international kind of attention. And now I chair the Digital Privacy Initiative for IEEE, where we're looking at an international level to set up a lot of the boundaries to answer those questions. But things that we had to develop in the technology from the ground up is like every operation, every transaction has a public and a private categorization, and you tag the data, whether it goes on the chain or whether it has to be held privately offline, and then what to do with it becomes the question after that, or as different parts of that. And what is required, we went through the pandemic learning that certain things are socially, we overpower and override, and you have to have these things public so that we can all find out who has a disease and the numbers and everything. But what are your rights in that balance? And those are kind of the privacy questions, and led to a whole governance architecture with 42 dimensions of governance that you can find in my dissertation if you pull that up. But this will be applied many places because it really mimics the real world, how we manage our government as addressed into technology applications and putting it into operation. So also a very exciting piece of what I've done. And I think more of what I will give to the world is along that lines than even the technology piece, because that's where really I think we're making a difference in giving people those rights in the digital era.
This has been great. Thank you for these insights. It's a more complicated space than I realized. Before we let you go, can you sum up for us what should we take away from here? What should we be thinking about?
So it's time to get involved right now. We are in the process of tokenization, doing an initial token offering for the distributed ledger. Look for it. Come in. It's not an investment. It's a utility token. Sorry, forgot. But it is a way to get in early, and we're offering some discount rates as well on the cryptographic key management. Reach out to blockframetech.com, and we're bringing in vendors right now to integrate it into their product to design this next generation security today and have it in your next product release when it comes down the road. It's like I keep saying, I'm excited about it. And I think we're changing the world, but I'll let you make that decision. But come talk to us.
Andrew, that concludes your interview with Dr. Gorog. Do you have any final summary about what we talked about here to leave us off?
Yeah, I mean, to me, it's all about device networks. backing away just a moment, the biggest denial of service attack in history, if you recall, a year ago or so, 2 years ago, was because internet-connected household cameras had defects that were exploited, and all of them attacked, one or two sites on the internet at the same time. Not an example of trust. That's an example of just scale. The scale we're talking about is, the number of these devices out in the world are just getting more and more, and a lot of them are internet connected. And when we connect an incredible number of devices across the internet, there's privacy issues, there's verification issues. Are these power readings that I'm getting from rooftop solar producers in my geography, are these readings real? Should I really pay these people? Are these traffic sensors from the neighboring city that say I've got a problem coming my way, there's a traffic jam coming my way, take corrective action? Are these real? We're talking about trust, we're talking about scale, the unprecedented scale. We're talking about interoperability between vendors and utilities, between utilities and other utilities, and probably even other applications that I just don't get yet. It looks like a kind of technology that we're going to see more and more of on the internet, and with industrial and other kinds of applications going forward. So it's a space that I've tried to ignore, and I don't know that I can anymore.
Okay, well, thank you to thank you to Dr. Christopher Gorog for speaking with you, Andrew. And Andrew, as always, thank you for speaking with me.
It's always a pleasure. Thank you, Nate.
This has been the Industrial Security Podcast from Waterfall. Thanks to everyone out there listening.